Some mountains feel different, not because they look taller or sharper or more dramatic in photos, but because they keep producing the same story over and over. Gold districts, copper belts, tin fields, rare earth clays, gem gravels, industrial minerals. Places where people can dig in 5 different valleys and still find evidence of mineral wealth. It's tempting to call that luck, but ore districts don't form by luck. They form by architecture, the deep geological architecture of a region built over millions of years, then exposed by erosion. When I hear people say, that mountain range is rich, what happened beneath that mountain range that repeatedly created heat, fluid flow, reactive rock, pathways, the 4 ingredients that concentrate metals? Because that's what an ore district really is. A region where Earth ran the same metal-making process again and again, long enough and large enough to matter. Here's the first thing that makes this topic click. Metals aren't the rare part. Concentration is the rare part. Most crustal rocks contain trace amounts of copper, gold, nickel, cobalt, tin, tiny amounts distributed everywhere. If the Earth never concentrated those metals, mining wouldn't exist. We'd just be breaking R. So the reason some mountains are rich is not that they contain more metal in some magical way. It's that they contain the right conditions to concentrate metal into deposits. And concentration requires a transport system. In geology, the most common transport system for metals is not a river. It's hot water. Hydrothermal fluids, water carrying dissolved ions, are the great movers of metal. They can leach metals from huge volumes of rock and redeposit them where conditions change. This is how you get veins, replacements, skarns, porphyries, massive sulfides, most of the deposit types that define ore districts. So if you remember one core idea, make it this. Ore districts are places where heat drives fluid flow through rock that can react, along pathways that stay active long enough to build deposits. Heat, fluids, reactive rock, pathways, time. Now the question becomes, where do those 4 things come from? They come from a few repeatable tectonic environments, Earth's big engine rooms. And this is where my personal opinion comes in. Most people look at mountains and think topography. Geologists look at mountains and think history. A rich mountain belt is usually a belt that has lived through multiple episodes of subduction, collision, rifting, magmatism, faulting, and uplift. Not once, repeatedly. Because every major tectonic episode has the potential to create one of the 3 big metal factories. Factory 1, magma-driven systems. Factory 2, sedimentary basin systems. Factory 3, metamorphic and deformation-driven systems. And ore districts often happen where these factories overlap in space or time. Let's make those factories feel real. Magma-driven systems, the heat engine. When magma rises and stalls in the crust, it brings heat and volatile-rich fluids. Those fluids can carry copper, molybdenum, gold, silver, tungsten, tin, and more. As the intrusion cools, fluids separate, fracture networks form, and metals can be deposited in large volumes. This is why some mountain belts dominated by volcanic arcs and intrusive complexes host world-class copper-gold systems. Sedimentary basin systems. The chemistry engine basins aren't just places that collect mud. They can collect salty brines and organic-rich layers. Under pressure and heat, those brines move through porous rocks, dissolving metals and redepositing them where chemistry changes. This is how you get many lead-zinc systems, uranium deposits, and sometimes copper systems in sedimentary settings. Metamorphic and deformation-driven systems. The pressure engine when mountains form by collision, rocks get squeezed, heated, and deformed. Fluids are released from metamorphic reactions and are pushed through faults and shear zones. Those fluids can carry gold and deposit it in structurally controlled veins. This is one of the classic ways you get gold belts. So the mountains that are rich are often those that have a history of subduction-related magmatism or collision-related metamorphism and faulting, or large basins that move brines, or, most powerfully, some combination of all 3. Now, even in a perfect tectonic environment, you still don't get an ore district unless the plumbing works. And the plumbing is structure, faults, fractures, shear zones, fold hinges. These are the pipes that move fluids. Without them, metal-rich fluids don't focus. They stay diffuse. That's why ore deposits cluster along long-lived fault systems. A fault that reactivates over and over is like a highway that never closes. Every time it opens, fluids move. Every time fluids move, there's another chance to deposit metal. This is also why ore districts often form in belts, not dots. Belts of faults, belts of intrusions, belts of altered rocks. And that brings us to the second idea that explains rich mountains better than almost anything else. Ore districts are not single events, they are cumulative. A region becomes rich because it experiences multiple pulses of mineralizing activity. Maybe the first event creates a copper system. Later, deformation remobilizes fluids and adds gold veins. Later, erosion concentrates the gold into placers. Suddenly, the same region has multiple deposit styles stacked in time. That's not randomness. That's geological layering. So when you stand in a mountain district and see old mine adits, gossans on ridgelines, quartz veins in shear zones, and placer gravels downstream, you're not seeing separate mysteries. You're seeing a chain reaction across deep time. And once you understand the chain reaction, rich mountains stop sounding mystical. They become predictable outcomes of a few powerful processes. If you could travel underground and watch ore deposits being made, you'd notice something immediately. The Earth doesn't concentrate metals in 1,000 random ways. It uses a few machines again and again. Each machine has a different fuel source, heat, chemistry, or pressure, and each one leaves a different fingerprint on the landscape. Machine 1, subduction and volcanic arcs. This is one of the most productive metal-making environments on the planet. When an oceanic plate sinks beneath another plate, it releases fluids into the mantle above. Those fluids lower melting temperatures and generate magma. That magma rises, intrudes, erupts, and cools, releasing metal-bearing fluids along the way. This environment is famous for deposits like porphyry copper, often with gold and molybdenum, epithermal gold-silver veins, skarns at the edges of intrusions, and a wide range of polymetallic systems. Why does this environment make ore districts? Because it combines enormous heat, huge magma volumes, long-lived magmatic cycles, and deep fracture systems created by tectonic stress. If you want a mental picture, think of a massive heat engine under the mountains, repeatedly injecting magma and fluids into the crust, repeatedly cracking rocks, repeatedly depositing minerals. When this happens for millions of years along a continental margin, you don't get one deposit, you get a belt of deposits. That's an ore district. Machine 2, collision and mountain building. When continents collide, the process looks slower and quieter on the surface, but it is brutally powerful underground. Rocks are buried, heated, metamorphosed, and squeezed. In that process, water is released from minerals, real water generated by chemical reactions. That water becomes a metamorphic fluid, forced through faults and shear zones. This is where many classic gold belts come from. Gold in these settings is often structurally controlled, hosted in quartz carbonate veins, associated with shear zones and major faults, and distributed in linear belts that track regional deformation. The richness here comes from long-lived deformation. A shear zone can stay active for a long time, pumping fluids repeatedly. It's not a single crack. It's a dynamic system that opens, seals, reopens, and seals again. This is also why these belts can have multiple generations of mineralization. A collision zone might later be intruded by magmas, adding new metal systems on top of old structures. Machine 3, rifts and sedimentary basins. Not all ore districts are born in fiery arcs or violent collisions. Some are born in basins, places where the crust stretches, subsides, and fills with sediments and fluids. Basins can generate and move brines, salty, metal-carrying fluids, through porous layers. If those fluids encounter chemical traps, such as reduced rocks, reactive carbonates, or mixing zones, metals drop out. This environment hosts major deposits like lead-zinc systems in carbonates, uranium in certain basin settings, sediment-hosted copper in some cases, and even some critical minerals concentrated by weathering and fluid flow. The big idea here is chemistry and permeability. Porous layers act like pipelines. Seals and traps focus deposition. The fluids don't need magma directly. They need pressure gradients and chemical triggers. Now, these three machines explain why the richest mountain belts are often those that sit near or within the scars of plate boundaries. But ore districts don't form just because one machine exists. They form because the machine has something to work with. And that something is the rock itself. The role of reactive host rock, even a metal-rich fluid can pass through rock and deposit almost nothing if the host rock doesn't react. Some rocks are chemically reactive, others are not. Carbonate rocks, for example, can be very reactive with acidic fluids. That's why you can get strong replacement deposits and skarns near intrusions where carbonates are present. Iron-rich volcanic rocks can also be reactive, providing sulfur and iron that help form sulfide minerals. Certain shales and organic-rich layers create reducing environments, excellent for dropping metals from oxidized fluids. So a rich district is often a place where the machine produces fluids, structures move the fluids, and the rock provides chemical traps. When those three line up, deposition becomes efficient. Now let's talk about the last ingredient that turns mineralization into an ore district: scale and repetition. One fluid pulse can create a vein. 1,000 pulses through a fault corridor can create a district. And this is why long-lived tectonic settings are so powerful. They keep reopening pathways. They keep refreshing heat and fluids. They keep adding layers of mineralization through time. That layering is what makes some mountain belts feel unbelievably productive. They aren't just rich in one commodity, they're rich in systems. If you fly over an ore district and look at where deposits sit, a pattern emerges. They're not scattered randomly. They line up. They follow structures. They follow intrusive belts. They follow basin margins. They follow contacts between rock types. They cluster near intersections. That's district geometry, how mineralization organizes itself in real space. Long-lived faults, the metal highways. Faults matter because they create permeability. But not all faults are equal. A fault that moved once and died might leave a fracture zone, but it doesn't build a district. A fault that reactivates through multiple tectonic episodes becomes a persistent pathway, a repeated channel for fluids. In many districts, the biggest deposits sit where major faults intersect, faults bend, fault stepovers create dilation zones, or faults cut reactive rock units. These locations create pressure changes in open space, making them ideal for fluid focusing and deposition. Intrusions, heat sources and fluid factories. In magmatic districts, intrusions are not just rocks. They are engines. They bring heat. They release fluids. They crack surrounding rock as they cool. They create alteration halos that can extend for kilometers. Many ore districts have multiple intrusions of different ages. Each intrusion can reactivate the system, reopen fractures, and add new pulses of mineralization. This is how a district can host both deep porphyry copper systems and higher-level epithermal gold veins, stacked vertically or laterally. Alteration footprints, the visible evidence of invisible processes. One of the most reliable district-scale clues is alteration. You can't always see ore minerals on a mountainside, but you can often see alteration footprints, broad rusty zones from sulfide oxidation, bleached rocks from chemical alteration, silica caps, clay-rich altered zones in volcanic terrain. Alteration is the shadow of the fluid system. It tells you where fluids moved, even if you don't see metal directly. And rich districts often show alteration over large areas, not just around one vein. That scale is a hint of a large, long-lived hydrothermal engine. The trap principle: why metals stop moving. Fluids move metals until something forces deposition. Common triggers include cooling, pressure drop, boiling in shallow systems, fluid mixing, reaction with the host rock, redox changes, sulfur availability changes. Different deposit types emphasize different triggers, but the principle is the same. Metals only become an ore body where deposition becomes efficient and localized. So what makes a mountain belt rich is not only that it produced metal-bearing fluids, it produced repeated situations where deposition was triggered in the same corridors. And over time, those corridors become districts. Uplift and erosion, the reason we can find it. There's one more factor that doesn't create ore, but controls whether we can access it. Uplift and erosion. Many ore deposits form kilometers underground. Without uplift, they stay buried. Without erosion, they remain hidden. Mountain belts are often uplifted and eroded strongly, exposing deeper levels of the crust. That's why mountainous regions are often where ore districts are discovered, not because mountains magically create ore, but because mountains expose the record of deep processes. And erosion does something else. It creates secondary deposits. When a hard rock deposit is exposed, weathering liberates minerals. Rivers concentrate heavies. Placers form. Iron caps form. Supergene enrichment can upgrade copper zones near the surface. So a mountain belt can become richer in a practical sense through time, because erosion and weathering add new layers of concentration on top of primary mineralization. This is why some regions host hard rock ore, plus placer gold, plus altered gossans that point to sulfides, all within the same district footprint. It's the same story, told at different stages of exposure. Now, to make this feel concrete rather than abstract, it helps to think like a detective walking through a landscape. You're not just looking for a shiny mineral, you're looking for the signs of the machine, the heat sources, the fluid pathways, the reactive rock units, and the repeated structural corridors. That's what separates a random mountain hike from understanding why the district exists at all. When people hear ore district geology, they imagine you need a graduate degree to make sense of it. In reality, the core logic is simple, even if the details can get complex. You're asking 4 questions. Question 1, what was the tectonic setting? Was this region part of an ancient subduction zone, a collision belt, a rift basin, a volcanic arc, a metamorphic belt? You can't see plates moving today in ancient rocks, but you can see fingerprints, rock types, structures, volcanic sequences, intrusive bodies, metamorphic fabrics. The setting tells you which machine might have operated here. Question 2. Where did the heat come from? Heat can come from magma, from deep burial, or from both. Intrusions, volcanic rocks, and metamorphic grades are all clues. Heat is what powers fluid flow and chemical reactions. Without it, metal transport is weak. Question 3. Where did fluids move? You look for pathways, faults, shear zones, fracture corridors, permeable layers, contacts between rock types. District-scale mineralization almost always follows pathways that are visible in structure and geology, even if the ore itself isn't visible. Question 4. Where did the system trap metals? You look for chemical and physical traps. Reactive host rocks like carbonates, redox boundaries, areas of strong alteration, intersections and bends in major structures, permeability contrasts. Those traps are where deposits form, and in districts they repeat in patterns. This way of thinking also explains why some mountains are not rich. A mountain belt can be dramatic and still be poor in ore deposits if it lacks one of the key ingredients. No long-lived heat source, no repeated fluid pathways, host rocks that aren't reactive, or no structural focusing. Mountains are common. Ore districts are not. Ore districts are the places where Earth's metal-making machines had everything they needed for long enough at large enough scale. And if I leave you with one final opinion, it would be this. The most important word in the economic geology is not metal, it's system. Because when you understand systems, you stop being surprised that certain mountain belts are rich. You start expecting it, based on the history written in the rocks.